Most people think Albert Einstein was a genius from the beginning. He wasn't. Most people picture him the way the photographs show him. White-haired, wild-eyed, a warm smile curling at the edges. A man who seemed to have always existed in that state. Comfortable in his brilliance, at ease with being extraordinary. But that image came late. It came after decades of struggle, rejection, and a very long stretch of time when almost nobody took him seriously. There was a version of Albert Einstein that most history books skip over. A version that couldn't get a job. A version whose professors didn't like him. A version that sat alone in a tiny Swiss apartment, scribbling equations in the margins of notebooks, completely unknown to the scientific world. A version that nearly gave up. And yet this man, this struggling, overlooked, slightly awkward young man, would go on to dismantle centuries of scientific certainty. He would look at the universe and see something no one else had ever seen. He would change not just physics, but the very way human beings understand time, space, light, and reality itself. How does that happen? How does someone who barely passed his exams become the most important scientist since Isaac Newton? How does a man who was rejected by nearly every university he applied to end up rewriting the laws of the cosmos? The easy answer is genius. He was simply born that way. But that answer is wrong. Or at least, it's incomplete. And the real answer is far more interesting. Because the more you look at Einstein's life, really look at it, not the legend, but the actual person, the more you start to realize something strange, something almost paradoxical. The qualities that made him so difficult, his stubbornness, his refusal to accept what he was told, his almost irritating insistence on questioning everything. Those weren't obstacles to his genius. They were the source of it. He didn't succeed despite being different. He succeeded because of it. And that changes the story entirely. What if the man who changed physics was the one who refused to think like everyone else? What if the greatest scientific mind of the 20th century was great not because he followed the rules, but because he couldn't? That's the story we're going to explore today. Not the myth, not the legend, the actual human being. And what his life can tell us about the nature of discovery, the cost of brilliance, and the strange, quiet revolution that happens when one mind decides to see the world differently. If you enjoy slow, thoughtful history like this, consider subscribing. It helps the channel more than you think. Albert Einstein was born on March 14, 1879, in the city of Ulm, in the Kingdom of Württemberg, in what is now southern Germany. He was the first child of Hermann and Pauline Einstein, a middle-class Jewish family. Comfortable but not wealthy, warm but not exceptional in any obvious way. By all outward appearances, the Einstein household was ordinary. Hermann was an easygoing, slightly impractical man who ran an engineering business with his brother. Pauline was cultured, musical, and deeply devoted to her children. They were the kind of family that hosted dinner parties and argued about books and expected good things from their children without quite knowing what those good things might be. Albert arrived, and then nothing happened. Not for a while. He didn't speak until he was nearly 3 years old. Some family accounts push it even later, closer to 4. In a household where conversation was prized, where Pauline's piano playing filled the evenings with melody. This silence must have been unsettling. His parents worried. His grandmother reportedly found him dull. Someone in the family, at some point, reportedly called him slow. We don't know exactly what was happening in the mind of that quiet toddler, but we know what he said about it later. Einstein himself recalled that even as a child, when he finally did begin to speak, he had an unusual habit. He would repeat sentences to himself softly under his breath before saying them aloud, as if he were testing them, making sure the words were right before releasing them into the world. That's not slowness. That's something else entirely. That's the behavior of a mind that takes things seriously before it commits to them. The silence eventually broke, and what came out over time was a child with an extraordinary inner world. Einstein later described his childhood as rich with what he called a kind of wonder, a sustained, almost physical sense of amazement at the way the world worked. Remembered being 5 or 6 years old and his father showing him a compass. The needle, no matter how you turned the case, always swung back to point north. There was nothing touching it. No hand, no string, no visible force. And yet it moved, and young Albert was transfixed. He said later that this memory stayed with him his entire life. That something must be hidden behind things, he thought. Something deep and invisible. That idea that there is always something hidden behind things would become the guiding principle of his entire scientific life. School arrived, and school was a problem. Not because he was unintelligent, that much was obvious. He devoured mathematics. He was reading popular science books at 10 and working through university-level geometry textbooks at 12. His uncle Jakob introduced him to algebra and described equations to him as a kind of detective game, in which the unknown quantity was a mystery to be solved. Young Albert loved this framing. He threw himself into mathematics with a quiet intensity that bordered on obsession. But school was not mathematics. School was authority. School was memorization. School was sitting still and repeating back what you had been told and not asking too many questions. And that Albert Einstein simply could not do. The German school system of the late 19th century was rigid in a way that is almost hard to imagine now. Teachers were figures of absolute authority. Discipline was strict. Rote learning was the method. Students were expected to absorb, not to question, to accept, not to probe. For a boy whose defining characteristic was an almost unstoppable urge to probe, to push on things, to ask why, to sit with a question until it cracked open and revealed what was inside. This environment was suffocating. He sat in class and his mind wandered. Not because he was lazy, but because the class couldn't keep up with where his mind wanted to go. He was bored in the way that only genuinely curious people can be bored, not passively, not sleepily, but with a frustrated, restless energy that must have been quite visible to everyone around him. His teachers noticed. They did not interpret what they saw charitably. One teacher told him directly that he would never amount to anything. Another said his mere presence in the classroom undermined the respect of other students. These were not casual comments. These were the considered judgments of men in authority, delivered to a child who was already quietly uncertain of his place in the world. What does a child do with that? Apparently, Albert Einstein did what he always did with things that confused or troubled him. He sat with it. He thought about it. And then, slowly, over years, he decided not to believe it. The tension between Einstein and formal education didn't resolve. It escalated. By the time he was 15, the family had relocated to Milan, Italy, following another of Hermann Einstein's business ventures. Albert was left behind in Munich to finish his schooling. And, for a while, he tried. He really did try. But the school felt like a cage he was growing too large for. The teaching style, the rigid military atmosphere, the expectation of obedience. All of it rubbed against something fundamental in his nature. He wasn't rebellious in a loud way. He didn't cause scenes or pick fights. His resistance was quieter and, in some ways, more complete. He simply disengaged. At 15, he dropped out. Without telling his parents, he obtained a doctor's certificate claiming nervous exhaustion and simply left. He took a train to Milan and showed up at his family's door, announcing that he was done with German school. His parents were not pleased. He was 15, had no diploma, and had walked away from the only path that society recognized as legitimate. His father, always gentle but now genuinely alarmed, pressed him on what he planned to do. Albert had an answer. He wanted to study physics. He wanted to understand the nature of the electromagnetic field. He had been thinking about it for years. Hermann Einstein must have found this answer somewhere between touching and terrifying. Albert applied to the prestigious Swiss Federal Polytechnic School in Zurich, known as the ETH, without having completed secondary school. He was 16, 2 years younger than most applicants. He failed the entrance exam. He did exceptionally well in mathematics and physics. He failed almost everything else. This is a detail worth pausing on, because it gets at something essential about how Einstein's mind worked. He wasn't failing because he was incapable. He was failing because he had already decided, at 16, which parts of knowledge mattered and which ones didn't. Languages, botany, French literature. These things didn't interest him, and so he hadn't bothered with them. The parts that interested him he had pursued with fanatical depth. The result was a profile that looked bizarre by any standard measure. Brilliance and incompetence sitting side by side, in the same skull, taking the same exam. The ETH's director, recognizing something in those mathematics scores, recommended that Albert spend a year completing his secondary education in the Swiss town of Aarau before reapplying. Einstein agreed. And something unexpected happened. Aarau was different. The school there followed a more progressive educational philosophy, one that emphasized visual thinking, conceptual understanding, and the development of individual judgment rather than rote memorization. For the first time in his academic life, Einstein felt something loosening. He later described this year as deeply happy. He made friends. He bicycled through the countryside. He boarded with a local family and fell into warm, easy conversation in the evenings. And he thought constantly about light. It was in Aarau, at 16 or 17 years old, that Einstein first posed to himself the question that would eventually crack the universe open. He was walking one day, or perhaps lying in the grass. The details shift in different retellings, when he asked himself a simple question. What would it be like to ride alongside a beam of light? If I could travel at the speed of light, moving parallel to a beam, what would I see? This sounds like the kind of idle daydream a teenager might have on a sunny afternoon. It wasn't. This question, this specific imaginative leap, would 10 years later become the seed of the special theory of relativity. He returned to the ETH in Zurich, passed the entrance exam, and enrolled. University was better than school had been, but not by as much as Einstein had hoped. He still chafed against authority. He still couldn't force himself to attend lectures that bored him, even when those lectures were theoretically important. He preferred to sit in the apartment of his friend Marcel Grossman, who took meticulous notes and study from those. He spent long hours in the library, reading the original papers of the great scientists: Maxwell, Hertz, Boltzmann, rather than attending the professor's interpretations of them. His professors were not charmed by this. One professor, Heinrich Weber, who had initially liked Einstein, grew so frustrated with his former favorite student that their relationship curdled into something close to hostility. When Einstein graduated in 1900, Weber refused to write him a recommendation letter. This was not a minor setback. This was, in the academic world of that era, close to a death sentence. Without a recommendation from your professor, you couldn't get a position as an assistant. Without an assistantship, you couldn't advance in academia. Einstein applied for academic positions across Europe. He was rejected by every single one. He had graduated, he had his degree, and he had nowhere to go. The system he had spent years fighting had, in the end, found a way to fight back. But here is the thing about Albert Einstein. He was stubborn in a way that looked, from the outside, almost like indifference. The rejections stung him. His letters from this period show a young man genuinely worried, genuinely struggling. But they didn't break him. They didn't make him doubt the validity of the questions he was pursuing. They just made him hungrier. He didn't fail the system. He refused it. And now he would have to find another way. Before we follow Einstein into the years of obscurity that came next, it's worth slowing down and spending some time in a place that most biographies rush past. Because what made Einstein different, what made him capable of what was coming, wasn't primarily his mathematical ability or his memory, or any of the qualities we typically associate with academic success. It was something much stranger, much simpler, much more difficult to quantify. It was the quality of his curiosity. Einstein himself was quite clear about this. Late in life, when journalists and academics and schoolchildren all asked him the same question, "How did you do it? What was the secret?" he gave variations of the same answer in different words, but with consistent meaning. He said he had no special talents. He said he was only passionately curious. He said the important thing was not to stop questioning. People heard these words and nodded politely and assumed he was being modest. He wasn't, or rather, he wasn't being entirely modest. He was making a serious intellectual claim. He was saying that the specific quality of his curiosity, and the specific way that curiosity expressed itself, was genuinely and primarily responsible for what he had discovered. Not raw intelligence, not superior memory, not computational speed. Curiosity. Sustained, relentless, playful, serious curiosity. What did that curiosity look like in practice? What was actually happening inside Einstein's mind in those years of obscurity and struggle? It looked like thought experiments. Einstein was, by his own account, not primarily a mathematical thinker. This surprises people, because the results of his thinking, the equations, the formulas, are mathematical objects. But the process of getting to those results was not, for Einstein, mathematical at all. It was visual, it was physical, it was imaginative in the most literal sense. He would take a situation and he would place himself inside it. Not abstractly, not on paper, inside it. He would imagine what it felt like to be there, what he would see, what he would experience, and then he would push the situation to its extreme and see what broke. The light beam thought experiment is the clearest example. He had been fascinated by light and electromagnetism since he was a teenager. He knew the mathematics of Maxwell's equations, the equations that describe how light and electricity and magnetism all interweave. And Maxwell's equations predicted that light traveled at a constant speed, roughly 300,000 kilometers per second, through empty space, always. This was already strange enough. Most things we observe have relative speeds. A ball thrown from a moving train travels faster relative to the ground than a ball thrown from a stationary position. Speed adds up. That's just how motion works. But Maxwell's equations seemed to say that light didn't follow this rule. Light was always the same speed, regardless of the motion of the source or the observer. Physicists of the era knew this, but found it troubling and inconvenient, and mostly tried to explain it away with various workarounds and hypotheses. They were not, for the most part, willing to take the implication seriously. Because the implication was radical. If light always travels at the same speed regardless of the observer's motion, then something else must be changing. Something must be giving, and the only candidates were the things that seemed most fundamental, most unquestionable: space and time. Einstein took this implication seriously. He didn't explain it away. He sat with it. For years he sat with it. And he asked himself over and over what it meant. The riding alongside the light beam thought experiment was part of this sitting. If you could travel beside a beam of light at exactly the speed of light, what would you see? You would see the light frozen in space, a stationary, shimmering wave, hanging still in the air beside you. But Maxwell's equations said this was impossible. A stationary electromagnetic wave cannot exist. Light cannot stand still. So something was wrong. Either the speed of light was not actually constant, which the equations insisted it was, or something about the idea of what it meant to travel at the speed of light was wrong. Einstein suspected the second option, and he suspected it because he was willing to ask a question that most physicists at the time considered not just unanswered but almost illegitimate. He was willing to ask, what is time? Not what happens in time, not how we measure time, but what time actually is. Is it a universal constant, the same everywhere, ticking at the same rate for every observer in every corner of the universe? Newton had assumed this. Everyone had assumed this. It seemed self-evident, almost silly to question. Einstein questioned it. He thought about two people standing in different places, one moving and one still, each watching the same light beam. And he realized, slowly, through months and years of careful imagining, that if light always travels at the same speed for both observers, then time itself must be behaving differently for each of them. Time could not be universal. Time had to be relative. This was not a mathematical conclusion, at least not at first. It was a conclusion reached by imagination, by curiosity pushed far enough and sustained long enough that the universe itself began to yield its secrets. He still needed to do the mathematics. And in the years that followed, in rented rooms and borrowed libraries, with Marcel Grossman's notes and his own fierce concentration, he worked out what the mathematics looked like. But the mathematics was, in a sense, just confirming what the imagination had already found. This is the pattern. This is what his curiosity looked like. It didn't look like calculation. It looked like play. Like a man who genuinely enjoyed being confused, who treated every mystery as an invitation rather than an obstacle. There's a particular phrase Einstein used that I find myself returning to. He talked about his method as beginning with a kind of free play with concepts. Not with equations, not with data, but with concepts, with ideas held lightly, moved around, combined, reversed, stretched to their limits. He said this free play was the necessary first step before any real thinking could happen. We don't teach this. We barely value it. We tend to treat daydreaming and serious thinking as opposites. Einstein seemed to know in some deep part of himself that they weren't. His curiosity wasn't passive. It was active, directed, almost aggressive, but it was also genuinely playful. And that combination, the seriousness and the playfulness together, each feeding the other, was, I think, the true engine of everything that came next. By the time Einstein was 23, his situation was genuinely precarious. He had his degree from the ETH. He had his burning questions about light and time and electromagnetism. He had a notebook full of half-formed thoughts and a mind that wouldn't let him rest. What he didn't have was a job. The rejections from universities and academic posts had been thorough and humbling. His old Professor Weber, the one who had refused him the recommendation letter, had quietly seen to it that certain doors were closed. Einstein wrote dozens of letters to institutions across Europe, attaching his academic record, asking for even a modest position. The responses ranged from brief and polite to simply absent. It was his friend Marcel Grossmann who finally rescued him. Grossmann's father knew the director of the Swiss Federal Patent Office in Bern, a man named Friedrich Haller. Haller was looking for technical examiners, people who could evaluate patent applications for new inventions and determine whether they were genuinely novel and technically sound. Grossmann put in a word. Einstein applied. And in 1902, after a wait that stretched his patience almost to breaking, he was hired. He was a patent clerk, a junior technical examiner, third class. The scientific establishment had no place for him, and so he went somewhere else entirely. The patent office in Bern was a strange place to change the world. It was a government building, bureaucratic and orderly, full of paper and procedure. Einstein sat at a desk and evaluated the technical claims of inventors. New designs for machinery, electrical devices, mechanical systems. He was good at it, actually. The work required exactly the kind of rigorous, clear-eyed analysis that Einstein was naturally suited for. He could look at a technical description and see immediately whether the underlying logic held, whether the claimed effect would actually follow from the proposed mechanism. He got through his daily workload, quickly, and then he had time. Time was what he needed most. Time to think. He called the patent office his secular cloister. There is something almost monastic about the image. A young man sitting quietly at a desk, surrounded by the mundane machinery of commerce, his mind somewhere else entirely. Out beyond the office walls, out in the universe, riding light beams, asking what time really is. He worked from 8 in the morning. By noon, sometimes earlier, he had finished everything required of him. He would then, with a discretion that seems almost touching, slide his personal notebooks under the desk or behind an official-looking document whenever he heard footsteps approaching. He was, technically speaking, supposed to be working on patent applications during office hours. He was, actually speaking, rewriting the foundations of physics. The isolation was real. He was completely outside the academic world. He had no colleagues in physics, no seminars to attend, no professors to consult, no access to the informal networks of conversation and correspondence through which scientific ideas normally travel. He read the journals, but the connection was one way. He could absorb the work being done elsewhere. No one could absorb his. And yet, and this is one of the most remarkable aspects of the whole story, the isolation may have helped him. In the academic world of that era, there were certain questions you simply didn't ask. Not because anyone had forbidden them, but because the social and professional pressure of being part of an institution, of having colleagues and mentors, and a reputation to protect, gradually shaped what seemed like worthwhile territory, and what seemed like territory better left alone. The really fundamental questions, the ones that would have required questioning Newton, questioning the entire inherited framework of classical physics, were, without anyone deciding this explicitly, off the table. Einstein was not at that table. He was in a government office in Bern, with no reputation to protect and no colleagues to disappoint. He could ask whatever he wanted. He could follow an idea wherever it led, no matter how strange the destination. He later said that this freedom was essential, that working outside the academic system, free from the expectation of publishing quickly, free from the pressure of teaching and committee work and departmental politics, had given him something priceless, the space to sit with a problem until it was actually solved. He was not entirely alone during these years. He had Mileva Maric, a remarkable woman, a fellow physics student from the ETH, the only woman in his graduating class. They had fallen in love during their student years, fought with their families about it, had a daughter together before they were married. A child who disappears from the historical record in ways that remain painful and unclear. By 1903, they were married. They talked about physics together, argued about it, shared ideas across the kitchen table. How much Mileva contributed to Einstein's thinking in these years is a question that historians continue to debate, without a fully satisfying answer. What seems clear is that she was not nothing. She was a trained physicist. She understood the work, and she was there. There was also the Olympia Academy. This was Einstein's name for a small, half-joking, entirely informal reading group he had formed with two friends, Maurice Solovine and Konrad Habicht. They met in the evenings in apartments and read together. Philosophy, science, literature. Hume, Mach, Spinoza, Poincaré. They argued, they laughed. They stayed up late discussing whether the world is really knowable, whether our senses give us access to reality or just to appearances. These conversations mattered. The philosophy especially mattered. Ernst Mach, the Austrian physicist and philosopher, had written a devastating critique of Newtonian mechanics, arguing that many of Newton's foundational concepts, including absolute space and absolute time, were not physical realities but mental conveniences. You couldn't measure absolute space. You couldn't point to absolute time. If a concept couldn't be operationalized, couldn't be connected to actual physical measurement, then maybe it shouldn't be a foundational concept at all. Einstein read Mach and found a kindred spirit. Or perhaps it's more accurate to say he found permission. Permission to question what no one else in the physics world was willing to question. Permission to ask, what is time really? What is space really? What do these words actually mean when you strip away the assumptions? The most important ideas, it turns out, didn't come from universities. They came from a government office in Bern, and an informal reading group that called itself by a joke name, and a man who had been told again and again that he didn't belong. In 1905, Albert Einstein was 26 years old. He was still a patent clerk. He was still outside the academic world. He was still, in the eyes of the physics establishment, essentially nobody. And, in the course of a single year, he wrote 5 scientific papers that collectively changed humanity's understanding of reality. 5 papers. 1 year. 1 person, sitting at a desk in Bern. Historians call it the Annus Mirabilis, the miracle year. The name is borrowed from 1666, the year Isaac Newton, confined to his family's farm during a plague, developed calculus and his theory of gravity. The comparison is apt. These are perhaps the two most productive years in the history of science, and both happened not in universities or laboratories, but in isolation, during periods when the normal structures of academic life had been suspended. Let's slow down and spend time with what Einstein actually did in 1905. Not the mathematics, the ideas, because the ideas are strange and beautiful, in a way that no amount of mathematical notation can fully capture. The first paper was about the photoelectric effect. This is the phenomenon by which certain metals, when struck by light, eject electrons. The strange thing was that the effect depended not on the intensity of the light, but on its frequency, its color in everyday terms. Dim violet light could knock out electrons, while bright red light produced nothing at all. Classical physics, which treated light as a wave, couldn't explain this. Einstein proposed that light was not just a wave. That light also came in discrete packets, chunks of energy, which he called quanta, following the work of Max Planck. And the energy of each packet was determined by the light's frequency. Violet light had high-frequency quanta with enough energy to knock electrons loose. Red light had low-frequency quanta that didn't. This was radical. Almost nobody accepted it at first. The idea that light was simultaneously a wave and a particle, that it had a dual nature that seemed to violate common sense, struck many physicists as absurd. It would take decades for the implications to be fully absorbed. Those implications would eventually become quantum mechanics, the theory that describes the behavior of the very small, the theory behind every semiconductor, every laser, every piece of modern electronics. Einstein would win the Nobel Prize for this paper, not, interestingly, for relativity, but for this. The second paper was about Brownian motion, the jittery, random movement of tiny particles suspended in liquid. Einstein showed mathematically that this motion was caused by the constant impact of individual molecules, and that by measuring the motion, you could actually calculate the size and number of atoms. This was the final proof that atoms were real physical objects, and not just mathematical conveniences. It settled a debate that had been running for decades. The third paper was about special relativity, and this is the one that required the most sustained attention, the one that had grown from that teenage thought experiment about riding alongside a light beam. To understand what Einstein did, you have to first understand what the problem was. By 1905, there was a deep crisis in physics. Maxwell's equations described light as an electromagnetic wave that always traveled at the same speed, 300,000 kilometers per second, through empty space. But this seemed impossible. According to Newton's mechanics, which everyone trusted, speeds were relative. If you ran toward a light source, you should see the light moving faster relative to you. If you ran away, slower. That's just how speeds worked. But when physicists tried to measure the speed of light from different positions and different directions, the speed never changed. It was always the same. Always. This made no sense. The Michelson-Morley experiment, conducted in 1887, had confirmed this result so precisely that it had become a source of genuine crisis. Either the experiment was wrong, which it wasn't, or something was deeply broken in the foundations of physics. Most physicists tried to fix the problem by adding something to the existing framework. They proposed the existence of the luminiferous ether, an invisible medium through which light traveled, which would explain why the speed was constant relative to that medium even as the Earth moved through it. They added mathematical correction factors, fudges, patches. Einstein did something different. He didn't add to the framework. He demolished it and rebuilt it from scratch. He started from two principles, just two. First, the laws of physics are the same for all observers moving at constant velocities relative to one another. Second, the speed of light in a vacuum is always the same, regardless of the motion of the source or the observer. He took these two principles and asked, what must follow from them? What does the universe have to look like if these things are true? The answer was astonishing. Time cannot be absolute. It must stretch and compress depending on how fast you're moving. An observer on a fast-moving spaceship, if you could somehow compare clocks, would find that time is passing more slowly for them than for someone standing still. This is not an illusion. This is not a measurement error. This is what time actually does. This effect is called time dilation. And it sounds like science fiction. It sounds like the kind of thing you'd find in a novel, not a physics journal. But it is real. It has been measured. Every time you use GPS on your phone, tiny corrections are applied to account for time dilation, because the satellites are moving fast enough and are far enough from Earth's gravity that time genuinely passes at a different rate for them. Without those corrections, GPS would be off by kilometers within a day. Space, too, was relative. Distances contract in the direction of motion for a moving observer. And mass and energy, which had always been treated as entirely separate quantities, turned out to be different forms of the same thing. This last insight became the most famous equation in human history. E equals mc squared. It looks simple. It is simple in the way that all great truths are simple once someone has thought to look for them. Energy equals mass times the speed of light, squared. What it means is that mass and energy are interchangeable. Every piece of matter contains a staggering amount of energy. The mass times a very large number, squared. A single gram of matter, if it could be entirely converted to energy, would release roughly the equivalent of a nuclear bomb. The sun shines by converting mass to energy in its core, continuously for billions of years. Einstein derived this not as a separate conjecture, but as a consequence of the rest of special relativity. It fell out of the mathematics almost as an afterthought. He published it in a short follow-up paper, only 3 pages, with a tone that reads, even now, as almost casual. He knew what he had done. He couldn't have known exactly how far the implications would reach. Special relativity was extraordinary. But Einstein already knew it wasn't complete. The theory described only a specific, limited case. Observers moving at constant velocities in a straight line, with no acceleration in the absence of gravity. This was a useful simplification, but it was a simplification. The real universe contained gravity. The real universe contained planets and stars pulling on each other across immense distances. And gravity was the one force that special relativity simply didn't touch. Newton's theory of gravity had dominated physics for over 200 years. It was one of the greatest intellectual achievements in human history. A single equation that described, with extraordinary precision, the motion of the moon, the orbits of the planets, the path of a cannonball, the fall of an apple. It worked. Magnificently, reliably, it worked. But it had a flaw, a deep philosophical flaw that Newton himself had noticed and that had bothered physicists ever since. In Newton's theory, gravity was a force, an invisible action at a distance. The sun reached across 150 million kilometers of empty space and pulled on the Earth, and the Earth pulled back. But how? Through what mechanism? What was actually happening in the space between them? Newton's theory gave you the numbers but not the answer. He famously wrote, "I feign no hypotheses." He could describe gravity. He couldn't explain it. Einstein spent the 10 years after special relativity trying to explain it. The problem consumed him. He later called the years from 1905 to 1915 the most intense period of his life. More intense, even, than the years that produced special relativity. He made wrong turns. He published papers he later had to retract. He grew genuinely uncertain at several points whether the problem was solvable at all. And then, at some point during this decade of struggle, he had the idea he later described as the happiest thought of his life. He was thinking about what it would feel like to fall freely under gravity. If you were in an elevator and the cable snapped and you were falling, not hitting anything, just falling freely, you would feel weightless. You would float. Every object in the elevator would fall at exactly the same rate. And, so relative to you and the elevator walls, everything would appear to hover. You couldn't tell, from inside that falling elevator, whether you were falling under gravity or whether gravity had simply switched off. This is the equivalence principle. Gravity and acceleration are equivalent. They cannot be distinguished from the inside. And this simple, elegant observation, this thought experiment about an elevator, became the cornerstone of general relativity. What Einstein built from this insight is one of the most beautiful theories in all of science. I want to try to give you a feel for it, because the full mathematical machinery is immense. It took Einstein years to develop with the help of his friend Grossman, who knew the relevant mathematics far better than he did. But the core idea can be grasped without equations. Imagine a stretched rubber sheet, flat, taut, smooth. Now place a bowling ball in the middle. The rubber sheet curves down around the ball, creating a depression. If you now roll a smaller ball across the sheet, it doesn't travel in a straight line. It curves toward the depression. It orbits the bowling ball. This is an analogy for general relativity. Space, or more precisely, the four-dimensional fabric of space-time, which combines 3 dimensions of space with 1 of time, is not a neutral stage on which events occur. It is an active participant. It curves. It bends. And what we experience as gravity is not a force acting across space. It is the curvature of space-time itself. The Earth doesn't orbit the Sun because the Sun is pulling on it with an invisible force. The Earth orbits the Sun because the Sun's mass curves space-time around it. And the Earth is following the straightest possible path through that curved space-time. The path looks curved to us from the outside. But from the Earth's perspective, it's the most natural path available. Gravity, in general relativity, is not a force. It's geometry. It's the shape of space. Einstein completed the theory in November 1915 and presented it to the Prussian Academy of Science in a series of papers over 4 intense weeks. He was 46 years old. He had been working on this problem for a decade. When he finally submitted the last paper, the one with the complete field equations, he later said he was so excited he couldn't sleep for 3 days. The theory made specific, testable predictions. One of the most dramatic was that massive objects, stars, for instance, should bend the path of light passing nearby. Starlight grazing the edge of the sun should be deflected by the curvature of spacetime the sun creates. To test this, you would need to observe stars near the sun during a solar eclipse, the only time stars near the sun are visible, because the moon blocks the sun's glare. The British astronomer Arthur Eddington led an expedition to observe the solar eclipse of May 1919. The measurements matched Einstein's predictions with remarkable precision. The news spread around the world within days. The Times of London ran the headline, "Revolution in Science." Einstein went from being known to being famous. And from that point forward, nothing about his life was quiet again. If you've made it this far, you're a part of a small group that enjoys thinking deeply. You might want to subscribe. There's a lot more like this coming. The fame was immediate, overwhelming, and deeply strange. Einstein had spent years in obscurity. He had grown accustomed to working alone, to the quiet of the patent office, to the small circle of friends who understood and cared about what he was doing. The world outside that circle had no particular interest in him. Then, suddenly, the world outside that circle could not stop talking about him. Newspapers ran profiles. Lecture halls were packed beyond capacity. People who had never opened a physics textbook and had no intention of ever doing so declared Einstein a genius, a revolutionary, the man who had overturned Newton. His face appeared on postcards. He received letters by the thousands, from scientists, from students, from admirers, from the simply curious, from the lonely and the lost who had attached their hopes to the idea of a man who could understand things others couldn't. He tried to respond to as many as he could. This was, by any measure, a mistake, or at least it was not sustainable. He spent enormous amounts of time in the years after 1919 simply answering mail. The misunderstanding ran deep. A story, probably apocryphal but too perfect not to mention, claims that a journalist once told Einstein that only 12 people in the world understood his theory of relativity. Einstein is said to have replied, "I cannot think who the 12 might be." Whether or not he said this, the sentiment was accurate. The popular understanding of relativity was essentially a void dressed up in confident words. People knew the name. They knew it was important. They knew it had something to do with time and space being relative. Beyond that, for the vast majority of admirers, the theory was simply a kind of modern magic, incomprehensible but authoritative, something to be gestured at rather than grasped. Einstein found this both amusing and melancholy. He had devoted his life to the project of understanding, to the belief that the universe was genuinely comprehensible, that human reason could actually grasp its structure. And now he was famous for having supposedly done this, while the actual understanding remained as remote as ever for the people celebrating him. He gave lectures. He traveled. He tried, in his clumsy, generous way, to explain. He told people that everything was relative meant nothing, that this was, in fact, a misunderstanding of the theory, which was precisely about identifying what was not relative, what was absolute, what didn't change regardless of the observer's position. But the misunderstanding had a life of its own. It was too convenient, too culturally resonant. People wanted a theory that said everything was relative. It confirmed what they already felt about the post-war world, the sense that the old certainties had dissolved. Einstein had become, in a very real sense, a cultural object, a symbol, something that could be picked up and used by people with completely different agendas, pointed in, whatever direction was convenient, its actual content irrelevant. He didn't love it. But he was also, to his credit, not entirely ungrateful for it, because the fame gave him something else, a platform. And Einstein, who had always had strong opinions about justice and peace and the responsibilities of those who understand things to speak plainly about what they understand. Einstein intended to use that platform. To understand Einstein's political life, you need to understand that it began earlier than most people realize. Long before he was famous. Long before the world was paying attention. He had grown up in Germany during a period of rising nationalism. He had watched the German universities, where he had felt most out of place, become increasingly chauvinistic, increasingly wedded to a vision of German identity that had no room for people like him. He was Jewish in a country where anti-Semitism ran through the culture like a current, sometimes underground, sometimes breaking the surface, but always present. When the First World War began in 1914, Einstein was in Berlin, having finally received an appointment worthy of his abilities, a prestigious position at the Prussian Academy. The war swept through the academic world like a fever. Almost every prominent German intellectual signed the Manifesto of the 93, a document defending Germany's conduct in the war, including the invasion of Belgium, which had horrified the rest of the world. Einstein refused to sign. He was one of 4 members of the Berlin academic establishment to refuse. He went further and signed a counter-manifesto, a declaration calling for European unity, for the renunciation of war, for a future in which nations did not settle their disputes by sending their young men to die in trenches. He wrote to friends about the madness of it, the tragedy of watching intelligent people abandon their reason to the service of nationalism. His pacifism was genuine, felt, and also, in a time of war fever, genuinely risky. He was accused of cowardice. He was accused of disloyalty. In a country heading toward one of the most destructive conflicts in human history, his refusal to participate in the enthusiasm was not merely eccentric. It was, to many around him, something close to betrayal. He didn't recant. He became, if anything, more emphatic. The rise of the Nazis in Germany, the late 1920s and early 1930s changed everything. The anti-Semitism that had always been present in German society was now state policy. Jewish scientists were dismissed from their positions. Jewish businesses were boycotted. The temperature rose year by year toward something that at first seemed unthinkable and was not. Einstein was abroad, in California, visiting the California Institute of Technology, when Hitler came to power in January 1933. He did not go back. He resigned his position at the Prussian Academy from a distance, donated his property in Germany to anti-Nazi causes, and eventually settled in Princeton, New Jersey, where he had been offered a position at the newly established Institute for Advanced Study. He became an American citizen in 1940. And then came the letter. In August 1939, Einstein signed a letter to President Franklin Roosevelt. It had been drafted largely by a young physicist named Leo Szilard, who had been one of the first to understand the military implications of nuclear fission, the recently discovered process by which the nucleus of a uranium atom could be split, releasing enormous amounts of energy. Szilard understood, with a clarity that was almost unbearable, that this process could be used to build a bomb. An unprecedented bomb. And he also knew that Germany had seized Czechoslovakia's uranium mines, and that German physicists were among the most advanced in the world. He was afraid Germany might be building one. He needed Einstein's name on the letter. Einstein's was the name that would make Roosevelt listen. Einstein signed. Roosevelt received the letter, and the chain of events that followed eventually led to the Manhattan Project, the American program to build an atomic bomb, and to the bombs dropped on Hiroshima and Nagasaki in August 1945, which together killed an estimated 200,000 people. Einstein's relationship to these events is one of the most painful threads in his biography. He did not work on the Manhattan Project. The American military considered him a security risk, too public, too leftist in his politics, and he was never given clearance. He was not in the room. He did not build the bomb, but his name had opened the door. His signature had started something, and he knew it. When he heard the news of Hiroshima, the words attributed to him were, "Woe is me." He spent the last decade of his life working against nuclear weapons. He spoke, he wrote, he lent his name to organizations and declarations and petitions. His final public act, signed just days before his death in 1955, was the Russell-Einstein Manifesto, a document calling on the world's governments to recognize the danger of nuclear weapons and to seek peaceful resolution of conflicts. It was signed by a group of distinguished scientists and dedicated to the proposition that the only choice facing humanity was peace or extinction, the scientist and the consequences, the idea and what it becomes in the hands of the world. Einstein spent the last years of his life trying to hold these two things together, trying to find some way to honor both the beauty of what he had discovered and the weight of what discovery can carry. He never entirely resolved it. Neither have we. There is a version of the Einstein story that ends in 1919, with the eclipse results and the world suddenly knowing his name. It's a tidy ending. Triumph following struggle. The obscure genius recognized at last. But Einstein didn't stop working in 1919. He had 36 more years to live. And those years, successful in some respects, celebrated in almost every respect, were, scientifically speaking, a long and increasingly lonely journey toward a goal he never reached. The goal was a unified field theory, a single mathematical framework that would bring together general relativity, the theory of gravity and the large-scale structure of space-time, and electromagnetism, the theory of light and electrical and magnetic forces. Einstein believed, with a conviction that never wavered even as evidence against it accumulated, that these two fundamental forces must be aspects of a single, deeper structure. That nature, at its most fundamental level, must be simple, elegant, unified. This belief was, at its heart, aesthetic as much as scientific. Einstein had always been drawn to mathematical beauty. He trusted equations that were elegant. He distrusted, on some deep level, equations that were complicated and patchy and full of arbitrary parameters. The universe, he felt, was not like that. The universe was like a piece of music. Intricate, yes, but intricate in a way that concealed an underlying simplicity. And it was his mission to find that simplicity. He worked on this problem for over 30 years. He published papers, revised them, abandoned approaches, started over. His colleagues watched with a mixture of respect and something close to pity. The physics world was moving on. Quantum mechanics, the theory that Einstein himself had helped launch with his 1905 paper on the photoelectric effect, had developed rapidly and was producing extraordinary results. It described the behavior of atoms and electrons and photons with a precision that was almost miraculous. But quantum mechanics was deeply strange. It was probabilistic at its core. It didn't say where an electron was, only where it was likely to be. It said, in a sense, that the universe was not fully determined, that certain events were genuinely random, with no prior cause that could in principle be identified. And Einstein could not accept this. He famously wrote that God does not play dice with the universe. He argued, against the quantum theorists, that the apparent randomness was not fundamental, that it was a symptom of our ignorance, that there were hidden variables we hadn't yet identified that would restore full determinism if we could find them. He was wrong about this, or at least the current evidence strongly suggests he was wrong. Bell's theorem developed in the 1960s after Einstein's death, and subsequent experiments have largely closed off the hidden variables interpretation. The universe does, it appears, play dice, or something stranger than dice. Einstein knew, by the end of his life, that he was isolated in this position. He knew that the younger physicists, the people who would carry the field forward, had accepted quantum mechanics and were building extraordinary things on its foundation. He respected their work. He didn't dismiss it, but he couldn't follow them there. It violated something too deep in his sense of how the universe had to be. He sat in his office at the Institute for Advanced Study in Princeton and worked. Alone, or with a small rotating cast of assistants, he filled notebook after notebook with attempts at unification. He tried approaches based on geometry. He tried approaches based on modified versions of general relativity. He tried things that required new mathematics that didn't yet exist. None of it worked. There's something both admirable and heartbreaking about this period. The stubbornness that had made him great. The refusal to accept the conventional answer. The insistence on sitting with a problem until it yielded. That same stubbornness was now keeping him inside a framework that the rest of physics had moved beyond. He was waiting for the universe to confirm his intuitions. And the universe, for once, was not cooperating. Even geniuses can be wrong. Even the greatest intuitions can mislead. Even the most productive stubbornness can become, eventually, a form of isolation. He knew this, I think. He was too clear-eyed not to know it. But he kept working anyway, because stopping would have meant something he couldn't quite name. Not defeat, exactly, but perhaps something worse. An acknowledgement that the universe might be less beautiful, less unified, less comprehensible than he had always believed it to be. We've been following Einstein's life through time, through school and obscurity, and the patent office and the miracle year and fame and war and the lonely decades at Princeton. But there's a question underneath all of this that we haven't fully answered yet. And it's perhaps the most interesting question of all. How did he actually think? Not what did he think, we've covered that. But the process, the mechanism. What was actually happening in Einstein's mind when he was working? Because the standard story, the story of the lone genius struck by inspiration, producing brilliant ideas from nowhere, is not only incomplete, it's misleading. It suggests that the process is mysterious and unreplicable. That Einstein was different in kind, not degree, from the rest of us. That what he did was magic. It wasn't magic. It was a specific way of thinking, a set of habits and approaches that can be described, examined, and in some cases even imitated. The most important of these habits was visual thinking. Einstein processed ideas primarily in images, not in words or symbols. He said this explicitly in a famous letter to the mathematician Jacques Hadamard, who was collecting accounts from prominent mathematicians and scientists about their mental processes. Einstein wrote that the elements of his thinking were not words or mathematical signs, but visual and muscular, images and feelings, certain signs and more or less clear images which could be voluntarily reproduced and combined. What this means in practice is that Einstein's thinking was, in a deep sense, physical. He didn't manipulate abstract symbols. He placed himself inside situations. He felt his way around them. He asked what things would look like, what they would feel like, what you would see if you were there. This is why the thought experiments mattered so much. The riding alongside a light beam, the freely falling elevator, the twins, one of whom travels at near light speed and returns, younger than the other. These weren't just pedagogical tools, ways of explaining ideas that had been reached by other means. They were the actual method. They were how he thought his way to the ideas in the first place. The second key habit was a willingness, almost a compulsion, to question fundamentals. Most people, most of the time, accept the basic concepts they use without examining them. We know what time is, more or less. We know what space is. We know what a particle is. These are inherited assumptions, absorbed from education and culture and common sense. Challenging them feels not just difficult, but slightly absurd, like being asked to question whether chairs exist. Einstein couldn't help challenging them. He was constitutionally incapable of treating an inherited concept as settled. He would look at a term, space, time, simultaneity, and ask, what does this actually mean? What observation, what physical measurement would I use to define this? What does it cash out to in terms of things I can actually see and measure? This approach, which he borrowed and deepened from the philosopher Ernst Mach, is called operationalism, and it's what led to relativity. The concept of absolute simultaneity, the idea that two events either happen at the same time or they don't, and this fact is the same for all observers, seemed completely obvious. Of course, some things happen simultaneously. What a strange thing to question. But Einstein asked, how do you know whether two events are simultaneous? You have to receive some signal, light, sound, something, from each event. And if you're moving, the signals reach you at different times than they would if you were standing still. So simultaneity is not absolute. It depends on the observer's state of motion. It sounds simple, stated this way. But no one had thought to ask the question before. The concept of simultaneity had simply been assumed to be fundamental and universal. Einstein asked what it meant, and the answer broke the framework. The third habit was what I'd call productive stubbornness. Einstein could sit with a problem for years, not making progress, not seeing the answer, not knowing whether an answer even existed, and not give up, not become demoralized, not decide the problem was unsolvable and move on to something more tractable. He described this as a need to understand, not a desire, a need, something closer to compulsion than ambition. He said, late in life, that he had no particular talent for mathematics, that some of his colleagues were far more skilled at the technical aspects of calculation. What he had was persistence, the willingness to come back again and again to the same question, to approach it from a slightly different angle each time, to keep looking until something shifted. And the fourth habit, the one that often gets overlooked, was a kind of cultivated strangeness toward the familiar. Einstein remained, throughout his life, genuinely astonished by things that other people had stopped noticing. He never fully lost the child's sense of wonder at the compass needle, at the way things worked, at the sheer improbable fact that the universe was comprehensible at all. He wrote, near the end of his life, that the most beautiful experience available to a human being was the mysterious, the confrontation with something that transcended ordinary understanding. And he meant this not as a mystical statement, but as a statement about method. The willingness to let things remain strange, to not immediately domesticate them into the familiar, was, he believed, the prerequisite for genuine discovery. He wasn't smarter. He thought differently. And the difference was not in the speed or power of his thinking, but in its direction, its patience, and its refusal to stop being surprised. There's a version of the Einstein story that focuses almost exclusively on the ideas: the light beam, the falling elevator, the equations. It's the version that gets told in physics classes and popular documentaries. It's accurate as far as it goes. But there was a person living that story. A person with relationships and obligations and emotional needs. And that person's experience of his own life was, in some respects, much harder than the triumphant narrative suggests. Einstein was not, by the accounts of those who knew him well, an easy person to be close to. He was warm in his way, genuinely kind to strangers, patient with students and correspondents, capable of real tenderness in his letters to friends. But he was also, in the specific ways that intimacy requires, profoundly absent. His attention was elsewhere. It was always elsewhere. Somewhere out in the universe, following a light beam, sitting with a field equation. His first marriage, to Mileva Maric, ended in divorce in 1919, the same year he became famous. The divorce had been coming for years. The relationship had frayed slowly, under the weight of his absences, his affairs, the difficult circumstances of their lives together. They had 2 sons, Hans Albert and Eduard. Eduard, the younger, suffered from schizophrenia and spent much of his adult life in institutions. Einstein visited him rarely. He later said he didn't go because the visits upset him too much. Whether this was understandable human limitation or something harder to excuse is a question that doesn't have a clean answer. He remarried in 1919. His cousin Elsa, who was widowed, and who became, for the rest of his life, the practical manager of his household and his public appearances. Elsa loved him, understood what she had taken on, and navigated the impossible task of being married to one of the most famous people in the world, while that person's real attention was elsewhere. She died in 1936. Einstein's response was characteristic. He reported feeling strangely free. He said he'd been so used to her suffering, she had been ill for some time, that now he felt he could work again. He meant it without cruelty. But it says something about the hierarchy of his priorities. Friends described him as fundamentally solitary, not lonely. Solitude was something he sought and valued. He wrote about it with real warmth, about the pleasure of working alone, the freedom of not being obligated to the social rhythms of other people. He said that his violin and his sailboat were his closest companions, that they required nothing of him and gave him everything. His relationship with fame was similarly complex. He understood its uses. He was willing to be famous on behalf of causes he believed in: peace, Zionism in its early form, civil rights in America. He understood that his name opened doors and gave weight to arguments, but the fame itself was something he experienced as an intrusion. The crowds, the requests, the relentless press attention. These were interruptions, impositions on the time and quiet he needed to work. He dealt with this, as he dealt with most things, by withdrawing. He could be charming in public, genuinely charming, not performed, But he retreated quickly from the social world and seemed most comfortable in the small private sphere of his work and his music and his sailing. And there was something in all of this that was perhaps inevitable. The same quality of mind that allowed him to spend 10 years on a single problem, the same patience and depth and willingness to be absorbed, made certain kinds of ordinary human reciprocity very difficult. You cannot simultaneously be fully present to another person and fully present to an unsolved equation. You have to choose. And Einstein, without ever quite choosing consciously, almost always chose the equation. Great thinking comes with trade-offs. This is not a criticism, or it's not only a criticism. It's an observation about what it actually costs, in human terms, to do what Einstein did. To follow an idea for years, through failure and uncertainty, to its strange and beautiful conclusion. The people who love you may not always be able to follow you there. In April 1955, Albert Einstein was in the hospital in Princeton, suffering from an aortic aneurysm. He had declined surgery. He was 76 years old, and he told his doctors that he had done his share. He died on April 18th, in the early hours of the morning. He had asked for paper and pencil, and they were beside him. He had been working, almost to the end, on the unified field theory he never completed. By the time of his death, his name had become so thoroughly a synonym for genius that it had begun to lose its connection to the actual person. Einstein. The word meant something like brilliance so far beyond ordinary comprehension that it was its own category. A shorthand for the inexplicable. A proper noun that had become a common one. But what had he actually changed? Not in the narrow sense. Not the specific scientific results which we've covered, but in the larger sense. What is different about how we understand reality because of Albert Einstein? The most fundamental change is this. The universe does not look the same as it did before 1905. Not because Einstein added details to an existing picture, but because he changed the picture itself. Before Einstein, science operated within a framework inherited from Newton. The universe was a vast machine, orderly, deterministic, operating in absolute space and absolute time. Space was a fixed stage, the same everywhere, for everyone. Time was a universal clock, ticking at the same rate from one end of the cosmos to the other. Matter moved through space and time, obeying laws that were in principle fully knowable. The universe was, in principle, completely predictable. This framework was not wrong exactly. It worked. It built bridges and predicted eclipses and launched projectiles with reliable precision. But it was limited in ways that weren't visible until someone looked at those limits directly. Einstein looked directly. And what he found was that space and time were not separate, fixed things. They were aspects of a single dynamic entity, space-time, which curved and flexed in response to the presence of matter and energy. That time did not pass at the same rate for all observers. It depended on their motion and on the strength of the gravitational field they were in. That mass and energy were interchangeable. That matter was, in a profound sense, frozen energy, and that energy was, equally, a form of matter. That the geometry of the universe was not Euclidean and flat but curved, and that this curvature was what we experienced as gravity. This is not a minor revision. This is a different universe. The practical consequences cascade outward in ways that are almost impossible to fully trace. The nuclear age, both its horrors and its applications, follows directly from E equals mc squared. Every nuclear power plant, every medical PET scanner, every smoke detector, every carbon-14 dating technique, all of these trace their lineage to Einstein's insight that mass and energy are equivalent. GPS, as we've mentioned. The large-scale structure of the universe, the expanding cosmos, the Big Bang. General relativity is the theoretical framework within which all of modern cosmology operates. The black holes that we have now directly observed, the gravitational waves detected in 2015 by the LIGO experiment. Einstein predicted them both, a century before we could observe them. But the change goes beyond the practical. It goes beyond even the specific scientific results. Einstein changed our relationship to certainty. Before him, the foundations of physics seemed secure. Newton's laws had stood for 200 years, confirmed by every experiment. After him, no foundation can be considered permanently secure. Every framework, however successful, is provisional. Every certainty is a temporary convenience, waiting for the right question to make it strange again. He changed our understanding of what it means to understand. The universe, it turns out, is not the place common sense suggests it is. Time dilates, space curves, mass and energy transform into each other. The very fabric of reality is dynamic, not static. Understanding this is not simply a matter of accumulating more information. It requires a willingness to let go of inherited assumptions, to follow an idea to its logical conclusion even when the conclusion seems impossible, to trust the mathematics over the intuition when the two conflict. And he changed, or at least extended, what we know about how discovery works. The greatest scientific advance of the 20th century did not come from a well-funded laboratory or a prestigious university department. It came from a government office in Bern, from a man with a bad recommendation and a good question, and a mind that refused to treat anything as obvious. He didn't just change physics, he changed how we see the universe. And in doing so, he changed, a little, how we see ourselves. Subscribe if you want more stories like this. Not just what happened in history, but why it happened. There is a photograph of Einstein that I find myself thinking about. He is sitting at his desk in Princeton, late in life. He's older in this photograph than the famous pictures. No longer the young man of 1905, the patent clerk with everything to prove. He is old and white-haired and slightly rumpled, and he is looking not at the camera but slightly away from it, at something that isn't in the frame. He looks, in this photograph, completely absorbed. Not troubled, not triumphant, just deeply, quietly present to something inside his own mind. You get the sense that the photographer was almost irrelevant to him, that the camera could have gone off or not, and he would have been the same, sitting there, thinking. This is how I want to remember him. Not the wild-haired icon, not the symbol. The man at the desk, still thinking, still looking for something that might not be there. Because that image, the man who keeps thinking, who keeps looking, who refuses to stop even when the problem seems unsolvable and the years are passing and the colleagues have moved on. That image is true in a way that the icons and the legends are not. Albert Einstein was not, in the end, a vessel for abstract greatness. He was a person who had a specific relationship with curiosity, who could not, by nature or habit or some combination of both, stop asking what things really were, who found in that asking both the greatest triumph of his life and, in the later years, its greatest frustration. The curious thing about how we remember him, the thing that would have amused and saddened him in equal measure, is that we remember him for the answers. E equals mc squared, the bending of light, the curvature of space-time. We remember the results, the equations, the moment of revelation. But Einstein always said the questions mattered more. What is time? What is space? What would it feel like to travel alongside a beam of light? These were the engines. The equations were just where the engines took him. And there's something in this that extends well beyond physics, because we all live inside assumptions we've inherited and haven't examined. We all have frameworks through which we interpret the world, frameworks that work well enough that we've stopped noticing them. The water the fish swims in, the grammar we don't notice because we're too busy speaking. Einstein's life suggests, and I think this is its deepest lesson, that the most important move available to any human mind is the move from assumption to question. The willingness to stop and ask, wait, what does this actually mean? What am I taking for granted here? What would happen if I followed this to its logical conclusion? This is not easy. It goes against the grain of how minds normally work. Minds are built for efficiency, for pattern matching, for using inherited frameworks quickly and without friction. Questioning everything is slow and uncomfortable and often unrewarding. Most questions don't crack the universe open. They just sit there, unanswered, a little embarrassing. But some of them do. Some of them turn out to be the question that everything else was waiting for. The question that, once asked correctly, with enough patience and enough honesty, and enough willingness to follow where the answer leads, changes the picture. Einstein didn't give us answers, not primarily. He gave us a way of looking, a habit of seriousness, of patience, of genuine curiosity pushed far enough to become dangerous to the status quo. He changed the questions. And, in the end, for a universe as strange and deep as ours turns out to be, that was the more important gift. He sat at his desk in Princeton, still looking. The answer he was looking for, the unified field theory, the single equation that would bring everything together, never came. He died with his notebook open. But the looking itself was something. The refusal to stop, to settle, to declare the mystery solved when it wasn't. The insistence that there is always something hidden behind things. That the world, for all its apparent familiarity, is stranger and deeper and more beautiful than it first appears. He was right about that. At least about that. And maybe that's enough.